In our last lesson, 8.7 for Chapter 8, we're going to be talking about surface area. So some vocabulary will be kind of important to begin with. We see two different figures here. In the first diagram, we see a prism. And the bases of the pentagonal prism are the pentagons that you see that are in light blue. The lateral faces are the rectangles that connect those bases. For example, here would be one of, highlighted in green that is, the lateral faces. And you can see it's a rectangle. This is drawn to perspective so you can kind of see it. And then in the second diagram to the right, which is a pyramid, a hexagonal pyramid at that, the base is the hexagon, and in this case, the lateral faces are all triangles, not rectangles. So here again is an example of one of the lateral faces of the pyramid. So whenever you have prisms, the lateral faces are rectangles. Whenever you have pyramids, the lateral faces are triangles. And each of these figures, the prism and the pyramid, are named by their bases. So when I look at the base, that's why this prism is called a pentagonal prism, because the base is a pentagon, and this pyramid is called a hexagonal pyramid because the base is a hexagon. Next, when we're looking at surface areas, it's very important to take a look and break things apart. So in this prism that I see here, this box, this is a rectangular prism, and we can add each of the different pieces up together. And so what you'll notice is, I noticed that the box had 6 pieces to it, so I broke it up. You can see the first row has the front and the back, the second row has the left and the right, and the third row has the top and the bottom. And since they're all rectangles, what I did is I just found the area of each of the rectangles and I added them all up. So for example, the front and the back both have areas of 6. In the second row, the left and the right each have areas of 14. And then the tops and the bottoms each had areas of 21. And if I add all of those things up, what I notice is I get a grand total of 82 for my area. Again, don't forget that area is in square units, so if this was meters, we would have said 82 meters squared, so on and so forth. Now for cylinders, which we see on this page, it's a little more complicated, but we're still going to break it apart. And what happens is when you break it apart, what you'll notice is if you were to take a can and pull the label off, the label actually is a rectangle. And so off to the far right here, you'll see that label off the can, like a soup can or something. And the top and the bottom are both circles. So in order to find out the total area, you would take 2 circles areas and 1 rectangle's area and add them all up. From each of the circles, I see that since my radius is 4, I would have pi times the radius squared, or in other words, 3.14 times 4 squared, and that would give me a grand total of 50.24. Now the cool thing is the top and the bottom are exactly the same, so you have 2 of those. Then what I notice is when I peel that label off the top all the way around here from the soup can, because I sliced it down the middle, when I peel it back, the width of my rectangle, or in other words what we call the base, was actually the circumference of that circle when we straighten it out. So then I know to find the area of this rectangle, I take the circumference of the circle and then multiply it by the height of the cylinder. So let's look at how that works. I know that the circumference of this circle is equal to 2 times pi times my radius. So that's 2 times pi times 4. Or in other words, 8 pi which if I multiplied out, I would get an approximation of 25.12. That circumference that we saw all the way around the soup can is the same as the base of my rectangle. And then the height of my rectangle, the 10, we were given over here. So now I take my circumference, or which was known as my base, and I multiply it by 10. My end result is 251.2. I take my three pieces, I take my top circle, my bottom circle, and my rectangle, add all those up, and in the end, I find out that my total area is 351.68. So the big idea here is, when you're finding the area of a cylinder, you have two circles and a rectangle. The rectangle's length or base or width, whichever one you want to call it, is really the circumference of the circle, which we already know how to find. Don't forget, the base of that rectangle is the circumference of the circle. So two circles, one rectangle, add them all up, that's the surface area of your cylinder. In this fourth slide, we're going to talk about the surface area of a pyramid now. And so in a pyramid, what you'll notice is we have one base, and then we have all the lateral faces. The example here is a hexagonal pyramid, because the base is a hexagon. We learned earlier that we can find the area of any regular polygon. That was the formula, in case you don't remember, of area equals the apothem times the perimeter divided by 2. In this particular case, I know that my apothem is 2, as is evidenced down below right here. Remember, that's the same as the word height. If I want to find my perimeter is going to be one side length, which we see here to be 10, times the number of sides that I have, and since it's a hexagon, that's 6, and then we divide all of that by 2. And in the end, we find out when we do that we get a grand total of 60. So the area of my base, or in other words, this hexagon, is 60. Now, we move on to the lateral faces. This lateral face is a triangle. And since we have a hexagonal pyramid, we have 6 of these. And I'm going to tell you that for one triangle, we have a base of 10 and a height of 15. That means that if I want to calculate the area of just one triangle, I know that it's going to be the base, 10, times the height, 15, divided by 2. Or in other words, one triangle is 75. Now the problem is, I don't just have one triangle. I have 6. So I multiply this by 6, which is 450, I believe. So 6 times 5 is 30. Carry the 3, 42, 45. So I believe that's 450 for the total lateral surface area of the triangles. So that area, the 450, is what's being produced right here. 6 triangles at 1/2 base times height. And the 60 that we saw in brown for the base was the result of the area of the hexagon, which was 1/2 the apothem times the perimeter, or in other words, apothem times perimeter divided by 2. So split it up into pieces and then add them up in the end. I took somewhat of a shortcut by multiplying one triangle by 6 instead of adding up 75 6 times. In this last slide in our lesson for 8.7, we're going to talk about cones. Cones have a very specific formula. The area of a cone is kind of strange. The area of the cone is, of course, the bottom, which is the circle, pi times the radius squared. So that's the circle. We see that down below in the formula the way they write it as pi r squared. But then you also need to add on the cone piece that's wrapping around. And the way that they describe that is pi times r times L. L being what they call the slant height. So in this case, the slant height in our cone is this 7 thing. And the radius, as you can see from our diagram, is the 5. And then all you really have to do is plug the numbers in and you're done. So if I were doing our example that we see right here, translating what's happening, I would have pi times 5 squared plus pi times 5 times 7. And in the end, when I multiply that all out and add it, I would get a grand total of 188 roughly 0.8. So the first part, not so hard in the red. That's pi r squared for the area of a circle. That's the base of the cone. The other part, the pi r L, is the part how you check out the cone part of it itself. And the L stands for slant height. Not height, but slant height, all along the edge of that cone.